Okay, so we are going to start by going over this assignment from yesterday. Again, this was the side that we had done as notes. On the back, the assignment that I gave you guys was 1 through 4 and 1 through 6 on pages 39 and 40 respectively. So for the first part there, again, I'm going to run through these problems real quick just to make sure everybody has the correct answers. If you have questions, you can ask questions as I go along. So for number 1, we have. Okay. Did you already upload it? Go take the pass, yeah. All right, so on number 1, we have 2 triangles going from A to B. This is going to be an enlargement because it is getting bigger. And if we look at the side lengths, again, it doesn't matter if you look at the horizontal pieces or the vertical pieces. I usually, if there's more than one piece, I'm going to look at the smallest ones just because then I won't have to do as much simplifying in the end. So on here, the bottom piece was 3. The bottom piece here was 4. And again, we always do image over pre-image. So B is our image. A is our pre-image. So 3 over 4 would be our scale factor. And that's all you had to do. So now going over to number 2, we went from A to B. Again, definitely going to be an enlargement. We also had for the side length of A, it was going to be 3. The side length of B was 7. Again, B being the image goes on top. A is going to be on bottom. So our scale factor here is 7 over 3. You don't have to reduce this. You don't have to change it to a decimal. You can just leave it as an improper fraction, and that's fine. You don't have to do any extra work there. The only time you really have to simplify is if you're given a fraction where both values can be reduced. So on number 3, all right, going from A to B. Now this one's a reduction because it's getting smaller. If I look at 2 of the sides, this top one, we have 6 units. The top edge here has 3 units. So again, image over pre-image, that's 3 over 6, which reduces to 1/2. Number 4, again, from A to B, it's getting smaller. So this is a reduction. If I just look at the top edge, this one has a length of 4. This one has a length of 3. Again, image, so 3 on top. Pre-image, 4 on bottom. Can't reduce that, so it just stays 3/4. Now, something else that we said yesterday for an enlargement and a reduction, there is a pattern that has to stay true in order for something to be an enlargement. A scale factor for an enlargement has to be greater than 1. So for the 2 on top, both of those values are greater than 1. And we can tell they're greater than 1 because the numerator is greater than the denominator. For the bottom ones, they're both reductions. In a reduction, the value has to be between 0 and 1. And again, in both cases, the numerator is less than the denominator, so it does fall between 0 and 1. So again, those are reductions. So there's more than one way that you can look at this. And again, you could do your scale factor first, and then say if it's enlargement or reduction, or like I did on here, you can first say, did it get bigger or smaller, call it enlargement or reduction, and then find the scale factor. All right, same thing for 1 through 6. So on 1 through 6, you have, again, same 2 steps. First one is getting bigger, so that's going to be an enlargement. Our scale factor, now these 2 overlap, but this is a 2. This here has 4 units. So 4 over 2, again, image over pre-image. That does reduce. 4 divided by 2 is 2. So our final scale factor is just 2. Number 2, we have the 2 images from A to B. It's getting smaller, so that's a reduction this time. This one is a little bit tricky because of our B values here. So I'm going to look at the top edge since it's the smaller edge. On the top of this one, we have a length of 5. On the top of this one, it's not full units there. It's going to be 2.5 units. Now, when we write our fraction, it is fine to write the decimal in the fraction like that. So 2.5 over 5, because this will reduce to whole numbers, because 2.5 goes into both the top and bottom evenly. So this becomes 1/2. Yeah. Now, number 3. Again, going from A to B, it is getting larger. So again, enlargement. Oops, got my N. Enlargement. And then we have this length is 1. That length is 3. So again, 3 over 1 or just 3. For our next one, number 4, from A to B, it's getting smaller. So it is a reduction. If I look at the vertical lengths here, this one has 4, this one has 3. So this is 3 over 4, which again can't be simplified. So it's just going to stay 3/4. Number 5, from A to B is getting bigger. So again, enlargement. The length of A on top is 5. The length of B on top is 7. Again, image over pre-image. 7/5 can't be reduced, so it stays like that. The pass is out right now as soon as she gets back. All right. All right. Number 7. Sorry, not number 7. Number 6. This one is the only one that was a little bit different. All right. So we have no horizontal or vertical lines here. So if we want to do this based off of our sides, which is the only way that we know so far, we can look at the lengths, turn this into a triangle to do Pythagorean theorem, or we could use distance formula. I will almost always use Pythagorean theorem when I have a figure on a coordinate grid like this. So I have lengths of 3 and 1, the sides of that triangle. If I was to do the same triangle here, the length on this side would be 2, the length on this side would be 6. So I got to solve for 2 lengths. The first one, I'm using the 1 and the 3, 1 squared and 3 squared. 1 squared is 1, 3 squared is 9. Add them together and we get 10. Gotta get C by itself, so you have to take a square root. So we get the square root of 10. On the other side of this, for the big figure now, same type of steps. I have 2 and 6 as my sides. So 6 squared plus 2 squared. 6 squared is 36. 2 squared is 4. Add them together and you get 40. Again, get C by itself by taking a square root. So I have the square root of 40. If I set up my scale factor, I have my image over my pre-image. The image in this case was B again, so that was the smaller one. So I have the 10 on top, the 40 on bottom. Again, they're still both being square rooted, but they both reduced nicely. So we have 10 over 40, which reduces to 1/4. We can take the square root of 4, which is 2. Square root of 1 is just 1. So our scale factor here is 1/2. And again, since it's between 0 and 1, this is a reduction. All right. Any questions there? Yes. Number 2 up here, this one. All right. So on number 2, using the top edges, all right, I found that this was 5 and this was 2.5, right? So I wrote it in a fraction with that decimal, and I was able to reduce this because this 2.5 will go into 5 evenly. So I was able to say 2.5 divided by 2.5 is 1, 5 divided by 2.5 is 2. If I had used the bottom edge, this bottom edge is 3.5 for the small figure. For the big figure, it's 7. So I could have done the same thing there as well. I would have had 3.5 on top and 7 on bottom. Again, 3.5 goes into both of those evenly. So I could also still reduce that to 1/2. All right. Any other questions on that paper? So that was the homework from last night. All right. Then let's go on to the next thing that we're going to do. So give me a second. All right, so the new sheet that I just passed out, this is for ratios and proportions. Now, ratios and proportions are definitely something that you guys have done before, whether from algebra or even prior to that. You've talked about them several times, but the reason why we're bringing them back up right now is because we are talking about our similar figures. So this whole chapter is about similarity. We just looked at similarity transformations and used something called a scale factor. Well, a scale factor is in fact a ratio. All right. So a ratio, and the definition is up here. A ratio is a comparison of two quantities by division. Now you can do it a couple different ways. You can write it in words. So if A and B represented numbers, we can say A to B. You could say as a fraction, A over B, or using a colon, A to B. Now, when we do our scale factor, it's a little bit different because our scale factor is comparing two images. And we always compare the new image to the original image. And it always goes in that order. When we set up our ratios here, if we're writing them in words, again, you're going to do it in whatever order they appear. So first, we're going to talk about how to set up a ratio. And then we're going to talk about how to solve a ratio. So on the left side of the paper, on page 5, there is a couple different examples of setting up ratios. The first one is not really a geometry example. It's just using a sports example and some numbers. So it says in 2007, the Boston Red Sox baseball team won 96 games out of 162 games played. We're at a ratio for the number of games won to the total number of games played. So all we have to do is write the ratio in the correct order. They already used a key word in here. So it said number of games, 1, 2, the total number of games, right? So they're telling us what order they want us to write this ratio in. The number of games won to the total number of games played. So the first number is going to be the number of games won. So 96. How many games are played? Well, there's 162 that were played. And we can leave it just like that. Now, in the example, they go a little bit further. They actually say, all right, what does that actually mean? Well, when we write things as a ratio, you can also then talk about things in terms of like percents, right? So if you were to actually divide this ratio out, then it'll give you a percent of how many games they actually won. So there's different ways that you can use ratios. But again, the ratio itself is just the 96 over the 162. And we can leave it just like that. Now, in example 2, this is a little bit more of a geometry example. All right, forget about the figure for a second because we don't really need the figure. They gave us words, and that's all you're going to be given at the bottom. So it says the ratio of the measures of the angles in triangle JHK is 2 to 3 to 4. So they're actually comparing 3 different values this time. So you can compare 2 numbers, or you can compare more than 2 values in a ratio. So this one actually has 3 different values. So 2 to 3 to 4. What that means is that those 3 angles can be represented as variables, which are being multiplied by those 3 values. So 2x, 3x, and 4x. So if we were to draw a picture, it'd look like that. Now, once we have a diagram, it's a little bit easier to think about what we're actually going to have to do. We know that all the angles in a triangle add up to what? 180. So we know all of them add up to 180. So then we can take the 3 angles that we only know as a ratio so far. We have them multiplied by x. And now we can take those 3 angles and add them up to 180 to figure out what the actual angles are. So we're going to take 2x, 3x, and 4x. And they already did the work for us. So I'm just going to point to it. Add it up, set it equal to 180, and solve. So we combine all the values. You get 9x. 9x equals 180, divide off 9, x is 20. Is that the answer? No, because they wanted the actual measure of each of those angles. So we have to find each angle individually. So now that we know what x could be, we're going to multiply each of those values by those ratio numbers. So 20 times 2 gives us 40. 20 times 3 gives us 60. And 20 times 4 gives us 80. If we added all those up, it does add up to 180. All right. So again, that's how we can use that in a geometric example. So we're going to do 2 examples down here at the bottom. I'm going to use numbers 1 and 4 as examples. The other 3 that are there will be part of your homework assignment. Now, in number 1, it says, again, in 2007 Major League Baseball season, Alex Rodriguez hit 54 home runs and was at bat 583 times. What is the ratio of home runs to the number of times he was at bat? So again, home runs to number of times at bat. So home runs was the 54 over number of times at bat, 583. Don't have to simplify. I don't have to do anything else. That's all we need to do for that problem. That's it. All they're asking for is a ratio. Now, could you simplify it and figure out like percentages and things like that? Yes, if they asked you for it. But there's no reason on this problem to go any further. All they asked us for was the actual ratio, and that's it. That's the 2 numbers they're asking for, and they're being compared. You can stop there. On number 4, now 4 is asking for a little more information. This is another geometry example. So it says the ratio of the sides of a triangle. So instead of doing the angles, now they're doing the sides. Are 8, 15, and 17. So I'm going to draw a figure to go with this. I have one side's 8, so I'm going to say 8x. One side's 15, so I'm going to say 15x. And the other side's 17, so I'm going to say 17x. The perimeter, which is the total distance around the triangle, is 480. So now I can also write an equation. I have 8x plus 15x plus 17x equals 480. Add them all up. So let's see. I have 17. Add 17 and 15, you get 32. 32 then plus 8 is 40. So all 3 of these numbers together add up to 40. So I have 40x on that one side. How do we solve from there? Divide. All right. So all we got to do now is just divide off that 40. And when I divide off that 40, it's nice because I have a 0 at the end of both these numbers, so I can cancel those out. So now I just have 48 divided by 4, which is 12. Now, is that an answer? No. Again, they want to find the length of each side of the triangle. So you got to plug them back in. So we got to plug 12 in for x on each of those sides. So we're going to do 8 times 12. We're going to do 15 times 12. And we're going to do 17 times 12. So what 3 values do we have? So first, 8 times 12, 96. All right. 15 times 12. And 17 times 12. Good. And we're done. All right. So those are the 2 examples I'm doing for that side. Now, let's go over to the other side. All right. This one goes into a little bit more detail about now proportions. So we talked about a ratio. Ratio is comparing 2 numbers. A proportion is comparing 2 equal ratios. So anytime we're talking about a proportion, it's when you're saying 2 ratios equal to each other. And the reason why this is very important for this chapter is because whenever we have similar figures, we're going to have sides that are proportional. In the previous section, we were looking at scale factor, right? The scale factor is a ratio, and that scale factor is the same no matter what sides you look at. So it is always going to be proportional. The scale factor is equal on each and every side, meaning the ratio is the same for each and every side of those similar figures. So they're always going to be proportional. How does that help us for geometry? Well, if we know some of the sides of the 2 figures that are similar, we can solve for the missing sides using a proportion. So you've done proportions before. This goes into a little more detail than we really need. So there are names to the different parts of a proportion. We don't have to memorize those names. Over on what day was that? Tuesday. On Tuesday, your first assignment was to define a couple of vocab terms, and I had you define geometric mean. And you might see here, one of the words that we use is means. So we have means and extremes. Well, there is a geometric mean that's tied with this idea of solving a proportion. But next week, when we get to where our definition is in the book, I'm going to explain it slightly different because I think this goes a little too far. You don't really have to know the names, means, and extremes in order to do this. But just know it's dealing with a proportion. Now, let's actually go over solving a proportion. So look at example 1. They've already done the work, so I'm just going to work our way through this, and then I'll do some examples at the bottom. But we have solved this proportion. Well, when we solve a proportion, that's where we cross multiply. So on here, the 9 and the x are going to be multiplied. The 16 and the 27 end up getting multiplied. All right, and that's what they did here. 9 times x gives us 9x. 27 times 16 gives us 432. And then we solve. Divide by 9, and you get 48. Now, they use this term cross multiply all the time, and people get mixed up in a lot of different problems. The only time you ever use cross multiplying is if you have proportions that equal. And I don't even know why they call it cross multiply. Oh, I know why they call it, but I don't know why they teach it as cross multiplying. All it is a simple trick to do 2 steps at once. Because if you had 2 fractions set equal, what do you want to do? You want to get rid of the denominator. How do you get rid of the denominator? You multiply it over to the other side. That's all you're doing when you cross multiply. Here, we have 9 over 16 and 27 over x. So in order to get rid of x from this side, what do we have to do? Multiply it to both sides. It cancels off here. So it's just going to be multiplied with the 9. How do we get rid of the 16? We multiply it to both sides. So it cancels out here and gets multiplied with the 27. We're just doing 2 steps in one when we're cross multiplying. So it's no huge trick. You're just getting rid of the denominators and bringing it over to the other side through multiplication. All right, but also call it cross multiplying because that's how most people learn it. Down on example 2. Now they are applying this idea to the number of voters in this particular scenario. So let me just read through the example. So in politics, Mayor Hernandez conducted a random survey of 200 voters and found that 135 approve of the job she is doing. If there are 48,000 voters in the mayor's town, predict the total number of voters who approve of the job she is doing. So another place that we are going to use this a lot of times is with population, and we'll have some problems that also deal with something called population density, which is kind of similar to this idea here. So we have our numbers of who she surveyed, and we're saying it equal to the total numbers, all right, because they should be proportional. So voters who approve is going on top, all the voters go on bottom. In the survey she did, same thing. The voters that approved were on top, all the voters on bottom. Whenever we write a proportion with numbers that are similar, we want to make sure that we're following the same rules on both sides of that proportion for both ratios. So once we have the proportion set up, we can cross multiply and solve. We have x and the 200 get multiplied together on one side. We have the 135 and the 48,000 multiplied on the other side. And then it's just solving from there. So divide by 200 and you get your answer of 32,400. Again, same idea. On that one, you have to set up your own proportion on something like that. But you just have to make sure you're following the same rule each time. Putting the same number on top, same number on bottom for both ratios. All right, let's go down and do a example. Actually, we're going to do 2 examples. We'll do 1 and we'll do 3 on this side. So 1 is pretty straightforward. We have a couple numbers. They're already set up in a proportion. All we got to do is cross multiply. We're bringing the x over and multiplying it with the 1. We're bringing the 2 over and multiplying it with the 28. 1 times x is x. 2 times 28 is 56. That's our answer. That one was easy. Now, we will see some of these proportions as we go through the next few chapters that get a little bit harder. So number 3, we're going to have to do some distributive property. So first off, multiplying, again, the bases to the opposite numerators. So we have the 10 is going to be multiplied over to the x plus 22. That gets multiplied to that entire thing. All right. On the other side, we have the 30 and the x plus 2. 30 times x plus 2. That's a problem with this thing. It doesn't want to focus when it gets too close. Let me focus it again and try one more time. Yeah. Yeah. I think that's as good as it's getting. All right. So on this side, 10 times x plus 22, again, it gets distributed to both of those values. So 10 goes to x and to 22. So that's 10x plus 220. On the other side, the 30 goes to both of those numbers. So 30 times x is 30x. 30 times 2 is 60. We got to get like terms over to the same side. I'm going to go ahead and move the x value first. So we have the 10x over here. Subtract that from both sides. Gives us 220 equals 20x plus 60. Get the 60 over by subtracting that. Minus 60. 220 minus 60 is 160. And finally, got to get rid of that 20. So divide it off. The zeros can cancel out. So it's really just 16 divided by 2, which is 8. And that's x. All right. So your homework assignment. It's the remaining parts of those exercises at the bottom. So on page 5, all the numbers 1 through 5, we already did 2 of them. And then on page 6, 1 through 8, again, we already did 2 of those. So not a very long assignment overall, but that is your homework assignment. It is already posted on Canvas. I will upload this video later since I already went over the homework, and that's going to be included in the little video that I did. I don't want to post it before my next class this assignment is due. So like normally if I include like going over homework in a video, it won't be posted until after I have all 3 of my classes. But you will see a video attached afterwards. All right.